Hello everyone and welcome to today's webinar, aptly named Collisions. So today we'll be learning how to analyze potential collision alerts within the Geotab platform. We have myself, Aaron Jarvis, and I'm a manager in the strategic channel development area of Geotab, located in the UK, and our local expert, Paul Stobb, who is the solution engineer behind all of this, and he's the real expert, so I won't do him an injustice of trying to introduce him myself. So in terms of an agenda today, I'm going to give you a brief introduction, which we're in the middle of here, an overview of Geotab as a company very briefly, and some of our products, and then we'll move into Paul, who's going to really get into the detail of our collision analysis and all the data that supports it. As I'm sure you're all aware, Geotab is one of the world leaders in connected vehicles. Our strategy is to be the bedrock of the connected vehicle. We're an engineering company, started over 20 years ago now by an engineer, and that's really the core of what we do. In the UK, we have a great engineering team. We're based in London, and we also have an automotive office in High Wycombe. So we're covering the full spectrum of having our solutions engineers on hand in the UK to help you and your customers get into the detail of our reporting and special features like the collision reconstruction. And we also have the European hub here for the automotive division. So we have the team available on hand to reverse engineer the vehicles and really get into the techie detail of what we can do. So that leads me nicely onto the hardware. As I'm sure you're all aware, we use the Go 9 device, or the Geotab Go device, which is a great OBD-based device which can be attached to virtually any vehicle using a harness. That might be directly to the OBD port, that could be through an adapter which connects to another port, or if it's on plant construction equipment or anything like that, we have harnesses which allow a 3-wire connection. This device has been developed over the last 20 years, and this current iteration is market leading in the EV space. We believe that our accelerometer and gyroscope data makes us market leading in crash reconstruction, which we're here to talk about today, and is all an enabler for the software, which we'll talk about briefly now. As you're all aware, we have the Geotab platform, which is the fundamental front end that the end customer can use to manage their fleet. But also we have a ton of other products, from big data, data consultancy that we can offer, as well as our big data engine and the ignition platform, where our customers and partners can enter and play with the data. I focus on this area a little more today than on the kind of more general fleet telematics stuff, but obviously we are super competitive as a fleet management software provider. We have a great rules engine, we have thousands of reports available. Our platform focuses on our key pillars, productivity, safety, efficiency, and expandability. And I will now hand over to Paul, who's going to introduce himself and give you a real deep dive into collisions and everything to do with the data around that. So Paul, over to you.
Perfect. Thanks so much, Aaron. Yeah, so also a brief welcome to from my side. My name is Paul Stobb. I'm a solutions engineer working daily actually with the product itself, but on the other hand, I also work on the data side. So all the data which we collect daily, we have in a big data storage, and with that amount of data, we can do also so much more. Okay, so going to the first topic, which is the data related to collision itself. So as you know, like we have our OBD device, which connects to the onboard diagnostic, and we collect a variety of data. So from this pool of data, you will first have to derive what is actually interesting for you. So let's say you had an accident 2 days ago. You don't want to have a mass of data where you don't know what you want to look at, but you want to have a specific view already on the data where you can derive informations from. So giving you like a broad picture on what data we collect, I like to show this diagram, which gives a very good insight. So here on the left side, you see the raw data input from our device, which we put in 4 different buckets. We have the GPS bucket, we have the faults, the status, and the accelerometer data. Then from this raw data, which we insert in our platform, we derive and calculate new data, which we have exceptions on. So later on, you will see in this webinar how to create rules, how to then create exceptions in your platform. From those exceptions, you have new data values. So for example, from one exception, you will see how long this exception was active, for what distance, and so on. As well, on the other side, you have trip data. So let's say you have a trip from A to B, and you want to calculate certain aggregated values around this. So here's interesting: when the trip started, when it ended, was there a collision? Was the collision at the end of the trip, at the beginning? What was the average speed during that duration, and so on? And then lastly, we have another part of data, which is the reference data, which is more like input data, which we get into our system, like geospatial data from the map providers, as well as VIN decoding information. So also importantly to know, so you can put the device in any car, and our device will detect in which car it is and derive the information from it, right? So this VIN decoding is also one important step here. So only focusing on the collision data itself. For the GPS information, importantly is that we have a buffer. So we are buffering a certain amount of data. So actually 100 minutes of second by second GPS data logs are stored on the device itself. So those are 6,000 logs. And as soon as you have a collision, we are triggering to extract this GPS data in high quality and then send it to the platform. Because in your instance, when there's an accident, you want to really go into detail and see the trajectory of the trip itself, and then derive the best possible quality speed information. Again, as soon as there's an accident, we are sending 1.2 minutes of second by second data to the platform, and then you have detailed information. The other bucket is the fault data. So what could be there interesting? Interesting there could be information around the diagnostic board. So did the car itself send us some fault data? Was, for example, before the collision happened, actually the light bulb on in front? Was there some error shown in the OBD message? Information like this is also interesting. And as well, if the device itself was installed correctly. Then status information could be also very interesting. So on the status information side, you can see what was the cranking voltage during that event, right? Was there some experience, like some anomaly during the collision? What was the RPM, the revolutions per minute showing? So typically you're driving, let's say you're on a highway and you're driving, and then you have suddenly a crash. You will notice that the RPM might be still ongoing after the crash, but then it suddenly just stops. And then the accelerometer, you see here actually the values in X, Y, Z. So it's you can derive this information in 3 different directions, and this is important to understand actually what direction means what. So the X direction is here the forward-backward movement of the car. The Y direction is the sideward movement, and the Z direction is the up and down movement. So the next topic is the functionality surrounding the accelerometer inside the Go device. Here, I first want to explain to you how do we calibrate the accelerometer. So how do we derive the high quality of information our sensors collect? So the OBD device can be plugged in just by taking the OBD connector and plugging in the Go device. What we prefer, what we say is a better solution, is to do a professional installation, especially if you want to derive high quality acceleration values. So here what you do is you are getting a T-harness. So what you do is you put out the OBD adapter, you connect the T-harness, and then you connect the Go device itself at a frame in the car where it's stable. So the goal is here to really zip tie the device to a frame of the car where it's stable and it's not vibrating. This ensures the best quality data, and therefore you can also derive the best information. After this, the device is now securely tied to a frame of the vehicle, but the position of the device is, maybe it's like facing down, maybe it's facing up, right? So we need to first calibrate the accelerometer, and this process is done in the first trip. So as soon as you put ignition on, you start your drive, this calibration process will happen. And in this process, we try to understand in which direction the device is actually installed, right? So as you can imagine, the Earth force is always available. So we will always know where up and down is. So we always know that the G-force is in that direction. The problem what you have to face next is in which direction is X and Y. So where's front back and where's side to side. So this is happening during braking events. So as soon as you drive and you will do some normal braking events, this device will calibrate itself, and all this information, if the device is calibrated or this calibration process is still in progress, you can visualize and see in the Geotab platform under status messages. If you notice that there might be an issue, like the device is not calibrating well, you will see this as a fault in the section in Geotab. And if you have further issues, you can also always click on the community.geotab.com, and there you can post your problems. You will see other issues which are pretty similar, often already in there, so you will have some hints there as well. So next is the data quality. So maybe you've heard that. So we have a patent on a curve logic around the way we collect actually our data. We don't send every second information. For example, when you have the accelerometer, which collects data 100 hertz, so 100 times a second, it would be just way too much data if you would send all this data right away to the cloud. So what we do is we have a algorithm implemented which looks for the maximum error. So the same what you see here. Imagine we have here 46 points and we just want to really send the essential information. So all noise information which is not relevant, we don't want to send. So what this algorithm looks for is for the maximum error. So it takes always the starting and ending point, and then checks where's the maximum error the greatest. So that's the red line actually, and takes that point and takes as long those next points as long as the maximum error is below a certain threshold which we defined. So this increases for sure the quality of the data, and how good this algorithm or how good the granularity is, you can define on which plan those devices will be. So as soon as you are on the highest plan, the Pro Plus plan, we have here the best threshold for you. So we will send you even better quality. And also we can tweak this a little bit. So as soon as you are like a very interested customer or partner on the collision data, and you want to derive like very small collisions, we can still work something out and see how we can derive those things. As well, we have, just to mention, a video from our CEO who explains this curve algorithm, which you could just find on YouTube on our channel. And we have a blog post around this graphic as well, which goes through the details. Next one is the spatial direction. To really understand what happened at a collision, we need to understand what those accelerations mean. So behind those accelerations, there's always a physical force, and we need to understand what value comes up, what it actually means. So if we have a backward forward acceleration, so we have this one axis which is backward forward, we have this in the platform called acceleration forward or braking. So if this value is positive, we have a forward acceleration. So as soon as you hit the gas pedal, you will notice a positive acceleration value. If you are seeing a negative value, you will have an acceleration backwards, so you're braking in this instance. Then there's the next one, which is acceleration side to side. So here, importantly, if you have a negative acceleration side to side, you have a force to the right. If it's positive, it is to the left. On the up and down side, so you'll always notice if the car is stationary, there's a Z value, so acceleration up and down of 9.8, something around this value because of the Earth force, and it will really depend on your location of the vehicle. So firstly, it depends for sure if you're on sea level or if you're in the mountain, as well as on the inclination. So if you are standing with the vehicle on a mountain and it's inclined, you will have the Earth force actually also in one of the other spatial directions included. Next one, I'm working on this topic already 2 years and trying to improve the current detection. And we figured out that this issue can be getting as complicated as possible. So you might want to detect a big accident, right, where you have a big collision where you can see all the things which are destroyed at the car, or you can reconstruct it very well. But also you might be interested in smaller accidents. So maybe you're just parking your vehicle, and during your parking event, you are ditching into some other car, and you have now some collision on your vehicle as well as on the third party. Also, lastly, it might be interesting, your car is just parking somewhere and someone else is driving into the car. Then you can go even further, and you might be interested in how do scratches on your vehicle derive, right? So did someone just took his key and scratched the vehicle, or what happened there? And this project, which is on research, which we are doing, is really to see how far we can go. So to understand what's the limit, our accelerometer and the data inside understanding what we can gather around any incident where there's a collision can do. So we started this project, and we saw that the first thing what we had to do, we had to change a little bit our firmware. So here in this project, we are collecting further data. So we are collecting actually 100 hertz of data around any 1G event. So anytime you're triggering a possible collision, which could be derived from a very sharp braking, we are collecting more data. So we're collecting actually 100 values before and after. So 1 second before and 1 second after. And then we try to look at those instances and derive more information from those and really look into the patterns. So here, for example, on the left down, you see one collision which we did as a test for a vehicle which was standing, and you see the high quality resolution of a very, very short event. That's already all to this research project. If you're interested, or if you're a customer reseller and want to know more about this, and just feel free to reach out under this email. Good, then let's move into the MyGeotab collision functionality. So how can you use the MyGeotab platform and then derive certain informations? So the first one is setting up alerts and notifications. So let me walk into the demo platform right now. So here on the screen, you see the demo platform, which we use in Europe. Actually, it's the Geotab Madrid. And we are here in the map section of the system. What I first want to do now, I want to introduce you to the rules section and then set up a custom rule to detect an accident. So my first goal here would be that I want for my fleet to derive a rule which will send me in real time any possible collision with information to my email if something happens. So to do this, you can move to the rules and group section here, click on rules, and here you will see first the default rules which we have defined, or you can change them yourself by clicking the pencil. So here first ones are, for example, the driving behavior. So if you're doing harsh brakings, hard acceleration, or harsh cornering. On the safety as well, on the last one, you will see the possible collision part. And here you can see that this rule is currently actually on. You can turn it off or on, and if you have a new database, you probably have to turn it first on. This rule here will trigger whenever there's a 2.55, which is around 2.6, and will be recognized in one of the axes. So if you want to look into this rule, you can just click this pencil here, which will take you to creating a new exception rule from this default one. So you can just give it a new name, just like test possible collision. And here you can change the color. So this will actually change the exclamation marks and the coloring of the trip data. And you can make it visible or not visible. You can have this rule inside a certain group. So for example, you only want this special rule applied to smaller vehicles, because the collision threshold might be bigger or smaller at certain vehicle types, right? So you can just define this rule to serve for a certain group of vehicles, and then define that here. I will not do that here, but just for you to know. Next one, you see here the conditions. So here in the condition part, you can define when this rule will actually be applied. I like to use this standard format as well, but you can also read this here. So here basically what it says is, if there's status data from diagnostics with acceleration forward or braking above 2.55 G, or status data acceleration forward or braking below minus 2.55 G, it will trigger, or in another instance, if acceleration side to side is above 2.55, or if the status data diagnostic acceleration side to side is below minus 2.55. That's like the typical default rule which you can have here. But what you can do now, you can still add some more meta information, or change this rule as you like. So for example, to trigger not as many false alarms. So what could happen is you install the device by plug and play. So, and often the OBD location of vehicles, certain vehicles might be at the door. So every time you walk out of the car, you might hit the device. And every time when you do this, you will get a notification now if you set it up. If you don't want to get those instances where the speed is 0, you can also just add this by saying, okay, I want only this triggered when this is over 0 kilometers per hour. And just by clicking add, you will have this already added here to the rule itself. Now to the sections around notifications. So how do you get this information to yourself? So on the notification side, we can add email. So you can get notified by an email. Just by clicking here, you can see here that you can add a template for this email. Here you just type in your email yourself, and then that's it. Also, you could do like driver feedback, you can create alerts, and you can do other things here. But I want to show you an example. So you're the fleet owner, you want to gather this real-time email around any possible collision of one of your drivers, and you want to see instantly interesting information for yourself. So where was the car, which car was it, and who was the driver, for example, things like this. You can add by going back to the rules, by adding a notification template. So when you click here to the notification template, you can just add a new template, add email template. You can give it a name. So test collision email, for example. You can give it a subject. I'll just give it the same subject. And here now you can define a body which will pop up in your email. So interesting for you might be first, okay, what was the device? So after this, you want to now fill in the device number. So you can just add this by using here the brackets. So this will automatically fill in this part of the email. Same, you want to maybe know the exact date when this rule got the exception, and as well the time. So I will just add those things here by clicking. You want maybe also get the speed and other metadata around the rule. You can just add here. Won't fill this in now fully, but another interesting thing you can add is the map. So as soon as you click here on the map, this will actually give you a view of the location where this happened. Okay, saving this email template will give you now the possibility, if you are in the rule itself, to add this as the email template by just, again, clicking on notifications, add email, and then clicking on the respective defined email template. For example, here, the minor accident one. Then you just put in your email address and that's it. Good. That's it for the first part. So next is the collision reconstruction add-in. Often you might want to reconstruct an event, an incident that happened in the past. So you know of, okay, this accident happened on the 25th of April for this specific vehicle, and you want to derive what actually happened around this. Or you want to use a tool which helps you better condense having this information in one place. So therefore, we have developed this add-in called collision reconstruction, and you can just add this add-in by clicking on our marketplace here. That's the marketplace. So as I mentioned, we have here many more solutions, not only from Geotab itself, but also from our ecosystem, from other providers, since we want to give our customers really any possible way they could benefit in. So we can really generate more by having an ecosystem here and having other players, other partners adding their value to this platform, which we cannot show, right? So one of this, and what we add here is the collision reconstruction. You can find it also here, or you can just search by it here on the top. So all you need to do to add this add-in is click on the collision reconstruction and then install it here. For this platform, it's already installed, but you will find if you don't have it, just install it now here. And then let's go to this add-in. So what you do is under activity, it will pop up the collision reconstruction add-in. Let me redo this. So the initial screen you will see here is this screen. So collision reconstruction, it's still in beta. So we're actually working on a new solution, on an improved one, which I will briefly explain to you also after this one. But what you can do now here is you know when something happened, and you just want to like look it up now. So I will derive one example accident which we experienced in inside of Geotab actually, which was last year, March 24. So if you don't know the exact date, but okay, the customer said, or the driver said it was in that week, you can therefore just search for a certain time period. So I will search, for example, for the whole March of any possible collision. So anytime there was a point where there was a fault data sent to us, which indicated there was a collision, we will derive a report on here. So let's do this. So here I chose now to look for the whole March, find the latest collision, and this is what pops up. So in this report, first you will find the device information. So what vehicle was involved, what's the VIN, what's the time of the collision. So it was on Sunday, March 24, 2019 at a certain point in time. You will find the point of impact. This is derived from the highest point of acceleration, which we'll go through in a sec. And then you also have like a map view. So this incident actually happened on the motorway here. And if you have an incident like this with a speed at 28 kilometers per hour, you should really take a look, since this looks like not a false alarm or not a false accident. You can derive the trip history just by clicking here on the trip history, which gets you to that certain trip, and then analyze what happened around this accident. So as you saw on the map here, the vehicle was driving on the motorway, and that was the trip which ended then here at this location. So suddenly the car stopped on the motorway. That was the situation. Next, you can see the speed data. So as well, you can look into the speed information here. The speed information will show you more information indicating what happened during before, during, and after the event. So again, the event happened at exactly 6 p.m. 26:39, and this would be exactly at 39 at this instance here. And what you see here is the car was driving on this motorway, so it was above 80 kilometers per hour, 94, 100. It slowed down to 60, and then there was, from this point, there was a sharp drop of speed. And suddenly the speed increased again, and then it decreased again. Looks already suspicious. So the car was driving, and it was something happened here while it was slowing down, and then weirdly it was accelerating again. And then it came to a stop, and then it was stopping. So why did this happen? We could investigate further when we look into the accelerometer data. So as well, you can look at the RPM data, and this will show you how many RPMs you had at which point. But here I want to focus on the acceleration data. So for the acceleration data, you will find this example here, which looks already quite interesting. So again, we had the time of impact, which was at 26:39, so which was here, and this happened before. If you want to lay over the speed, you can just click on the options and click on show vehicle speed. This will add the speed as well. Now you just have to confirm what you want to see, and you can see now the sharp drop of the speed here. And after talking to the driver, I know what happened, and what the case here was. Actually, the car was seeing that there was a traffic jam in front of the car. Then it slowed down, and it got to an almost stop in front, and then actually someone from the back hit the car. That's why the car experienced a high acceleration to the front. So here you see a positive acceleration in X, in forward braking. So the car itself was accelerating at this point when someone crashed from the back into it. And then at the second instance, it crashed in front of it into another car. So here it got to a even higher crash, so more forces, so minus 62, which is 6G, which is already quite high. And then after this, the car got to a full stop. If we go back to the report, we see that the point of impact just indicates one section, and this is because we have the current configured just to show the highest impact location. So from this graph, you would notice that that instance is of higher magnitude. So what we did here is we showed the location of that highest impact. Exactly. Then lastly, you should always keep in mind that the GPS coordinates are only accurate to 2.5 meters, and that the speed is accurate to 3.6 kilometers per hour. You can export this PDF and have it printed as well if you click here on the export to PDF. As I mentioned, we are working on a new version for this. So for the new collision reconstruction 2.0, we have gathered reviews from our customers, and and saw there's much more value if we can present you instantly all those instances which we defined as possible collisions. So in the new version, which you will have available hopefully this summer, you will derive instantly for specific devices how many possible collisions there were on which dates, and then you can instantly go in those reports by just clicking the link. So if you click the link, you will get instantly in the report, and the report will now also include actually multiple impacts. So the incident which I just showed you, which had one location of accident, we would include here also that the crash actually happened also in the back right. So in those instances, you will see that there's two locations from the impact. Now walking into the next area, which I work on a lot, is also to derive what's the difference between the collisions. So not every collision you will notice in the Geotab platform which was created might be a collision, because it really depends on how good you install the devices, what happens around this. So as soon as you kick the device, you could trigger also an accident, right? And I want to now show you how you can filter out false detections and what are typical hints you should look at, so to see if it's false or not. So let's look back to this one incident I just showed you, because this is a true accident. If you have this incident in front of you and you want to have a check if it was a true or what true incident, you would first, in the best instance, look at the location itself. So was it at a installation location? Was it at a motorway? Was it at a parking lot? So very indicative is that it was at a motorway, which was very rare to have a false positive. So why would you hit the device maybe when it was on the motorway? Anyways, if you would have a professional installation, you can be sure that no one can hit the device or not. It cannot trigger otherwise. You will not have this issue as well, right? Next thing you should look at is the speed. So what was the speed during that incident? So if it's 0 kilometers per hour, that's also an indication, quite frankly, that this could be a false alarm. On the accelerometer data, going more into detail, this is representing the force itself, right? So if you just go on the max zoom level, you will notice that we have 2 exact peaks here. You have smaller peaks behind, and then you have no other instances here. This area below the peak shows you how much force was actually happening during that instance. For a crash, what we experienced, like we did some crash tests, it's often that when you crash into a car, you will have a first impact, and then after both cars like moving apart from each other, they slightly move again into each other, and then you could derive another impact right after. And also what you should take in mind is that after any crash, there could be vibrations or any physical force which you will notice and which will have a downward trend afterwards. So here as well. So that's a true incident, and now I want to move to a false indication as well. So for the false indication, let me just look into another instance from our team. So this false alarm actually happened, which we gathered on October 19. When I just go now to October and search for this instance on that vehicle, you will see the following: done, find latest collision. Okay. Again, you see the device information with the vehicle name, driver, vehicle information, time of collision. So this was on the 19th of October at 5:32:47 p.m. You see a different location now. It's not on a motorway, it's on a map. First, let's review the actual trip. So when moving to the trip history, you will notice that that was the trip itself. Let's look back when it was exactly, it was at 5:32:47. So the car was driving here and stopping there. And then we just check when was the exact stop of the vehicle. So the stop was at 4:54 actually, and we got this message at 5:32. So this was half an hour later, and therefore it wasn't moving during that collision itself. Okay, so that's a first indication. Next, we want to look into the speed and RPM data. So if there was no trip happening at the same point in time, and the speed was frankly 0, if we just check back on the speed here, you will find that there will be no speed available during that collision time, as well as RPM information. So we didn't get any RPM information, no speed, but we got accelerometer data, so that's why it triggered. So somehow this device sensed a 35 meters per second squared acceleration to the front. And if we click on the accelerometer, we will find this picture here. Again, we see some peaks, right? And let's now find the solution why this could have happened. So what you see here, if you just want to understand what's behind, you see first in red the forward of braking. So you'll find a negative acceleration here, so -15, then a first peak 34, then it goes down somehow again, up and down and up and down again. So this looks already kind of like a vibration, right? So it goes up, down, the same actually with the side-to-side acceleration, up, down, up, down. Still, the value which you see here, which is 34 meters per second squared, is not a typical value. So if you want to compare this to a normal movement of a car, which we could just do right now here, we just look how the vehicle moved the hour before because we saw the trip. You can just take this here. There was no acceleration really collected before, but maybe if we go a little bit further, also no acceleration. I can show you that example on a different vehicle. So this car wasn't driving that much on that day. Let's maybe move one day earlier. Yeah, so that's a typical example of a car if it's moving. So if the car is maybe turning around the corner, is doing some harsh braking or some normal braking, you will find a pattern which is equal to this one here. If you already zoom out, you see that this is way different compared to that instance. So this is not a normal driving behavior, but we know already it's also not an accident. And what makes me sure that it is not an accident is if you move further inside, you see again this pattern of up and downs. So you have a lot of zero crossings, so vibrations around this device. And then if you add the speed, you will see that the speed is 0 as well. Oh, that's for the day before. Here you won't see any speed for that instance here. Good. Yeah, that's all for this part. So keep an eye on those informations here and on the pattern itself, how it looks like. But also it's very hard always to only find this information out by yourself from looking at the data. So the contact to the driver and around the situation itself should be observed as well. In very harsh accidents where there might be even a fatality or anything like this, we also offer a service by our support team to do a in-depth data analysis. So this can be also done by just placing a support ticket to our support team. We covered everything, so I would be open now for the Q&A session.
Thanks, Paul. So we have a couple already, Paul.
Okay.
The first is from Trevor Harrison, who asks, how do we detect low impact crash if a vehicle is parked up without the engine on? Or can we, should I say? And if we can, how do we do it?
So currently our device, when the ignition is off, the device will be in the sleeping mode. So the device itself will not collect the high frequency acceleration data only if it wakes up. So to really detect damages when the car is stationary and parked and ignition off, we need like an instance that the device wakes up. So sometimes this happens, for example, when there's a very harsh crash to the car moves, and with this movement, the device wakes up, collects this data, and then sends it to our cloud, and then we can analyze. Those instances are very rare, I have to admit and say. So what we currently do is we're working on a solution to derive always when the car is off to also collect data. But that needs to be developed, and because here we need to be very careful that we don't drain the battery too much. So we're working on this.
Thanks, Paul. So another question here is, do we have any indication of why the false reading that you displayed happened? And I guess how would the fleet manager react to that?
Yes, if we go back to the graph here itself. So I would always first look at the trip itself. So was the car driving during that collision? If not, it was stationary, it was stopped. So if it was stopped, I would already look, okay, first you need to find out if it's a professional installation or not. So if it's professionally installed and the device is very hidden in the car itself, no one could trigger this by like getting out of the door or something like this. So there, in those instances, I would look very more in detail, talk already to the driver. But if it's like just a plug and play installation and the OBD location is like right at the door or something like this, and the car was parked, I would already assume it might be a bad collision or a false detection if the speed is 0, and I gather like a acceleration which is kind of like a vibrating pattern here. So always try to see if there was a normal collision, you would have like a the car was deaccelerating. You would have a, normally if it's crashing in the front, you will have a negative acceleration in red in forward braking, which would be of a higher area and not as like a vibration as here, which goes up and down, up and down, up and down.
Thanks, Paul. Another question from Robert is, do we have an indication of the accuracy of the crash data when the device is connected directly to the OBD port rather than using a harness?
So connecting to the OBD port directly or via a harness should not change the data quality. So if the adapter itself from the OBD is very, very good installed, so there's no vibration, it's the same. But the amount of data which you would gather over the onboard diagnostic is the same. So only thing is if the device is badly installed and it's moving during driving, then you would have less quality accelerometer data.
Thanks, Paul. And then the final question that I see now is, do we have any reference G values that you'd recommend as a threshold if we're using a 12 or a 24 volt asset? So I guess this is referring to not vehicles necessarily, or not cars.
Okay. Yes. So first, if you're looking at passenger cars, as you saw before on the rules side, it was 2.55, which is also when the airbag drops off. So the airbag itself, in the vehicle itself, they have all accelerometers implemented, and if they sense a high acceleration, they pop out the airbag, and we just looked at their rule, right? Vehicles with more weight, let's say heavy duty vehicles or trucks with load, heavy trucks, you will find less acceleration, which are that quickly deriving, right? Because they have just more mass. So in those instances, I would put the G-force to less. So for like a heavy truck, I would do it, for example, for 2G. But you always have to be also careful with heavy trucks or construction vehicles, because there, in those instances, you also have a lot of vibrations happening. So it could be that if you place the device close to a vibrating frame, that those patterns of vibration will trigger also those accelerations. If you, on the other hand, want to experience or play around more with like smaller damages than 2.5 G, for example, when you're parking your car and you want to then already sense if this could be a potential collision, I would recommend you do a professional installation, and then as well you can trigger this collision reconstruct or this collision event in the rules side already at roughly 1.2 G in any direction, forward braking and side to side.
Thanks, Paul. That leads nicely into a question by Gary Kirby, who asks about the accuracy rate of our collision detection. And I think I'll add the caveat to this. It seems today that we don't filter anything out. We capture all of the data and make that available, as long as there's an event above the G set within the rules engine. Do we have any plans to put, a filtering system in place to provide only positive crashes to the end user?
Yeah, that's a very good point, and that's the main issue what I'm actually working on. So to really give the best value back. So some customers might be interested only in the real ones, positive where there was a detection. Other ones might be interested if there's maybe the car was driving always over a pothole or something like this. So they maybe want to detect those instances as well. And we're working on with this research group, which I introduced, on detecting those instances. So separating heavy damages from smaller damages, from other patterns of, for example, if you have the device close to the door sitting and you just smash the door or close the door very quickly, and those can also trigger in some instances those patterns. And we're working on this. If you see that there's value, if you see that there are interested customers, what we do is we partner up with them, and they give us an insight on which events they are really interested in. And what we do is we look at those patterns and analyze those and derive a model, an algorithm to really sense those instances only.
Yeah, that's a really good point, Paul. So I'll reiterate Paul's earlier request. If you are interested in getting involved, or your customers or the rest of your company are interested in getting involved in that project, please send an email to Paul and probably your partner account manager as well, because as always, we're looking for customer and real world insight to build these machine learning models. So I'll use the next 30 seconds to give a little bit of a pitch. We're running these webinars weekly, so please look out in your inbox for future invites. And thank you all for joining. Thank you, Paul, for a very comprehensive view of collision detection, and I will draw the webinar to a close.
Thanks. Bye-bye.